Okay, let's continue with section 3.3. Last time I introduced the concept of CA and total CA, and the difference is that CA cares about the spatial pattern of the neighborhood. Instead of that, total CA cares about the sum of neighbors, right? So let's get back to the game of life. Now we know that it is actually a total CA, right? Because we can see the transition rules here. Any live cells with fewer than 2 live neighbors dies. So here, each cell we care, let's just assume the cell we care is live cell. It is affected by its neighbors. Is it affected by the spatial pattern of the neighbor? No, it is affected by the sum of its neighbor. If live is represented by 1, any live cell with fewer than 2 live neighbors dies, which means that if the sum of the neighbor is smaller than 2, then this live cell, its state will change to 0, because for now its live is 1. It will die. Then if it means that if the sum of its neighbor is smaller than 2, it will change to 0. So any live cell with 2 or 3 live neighbors lives, which means that for now the cell is 1. And if the sum of its neighbors is 2 or 3, then it will stay as 1 because it lives. Any live cell with more than 3 live neighbors dies. It means that if the current state of the cell is 1, but the sum of the neighbor is larger than 3, it will change to 0. The cell's value will change to 0. It dies. And if currently a cell is 0, but the sum of the neighbors is exactly 3, this dead cell will change to live. 0 will change to 1. So yeah, so now you know the game of life is a total CA. Is a total CA. Okay. Okay, let's continue. And next method to produce aggregation and segregation is called simple majority rules. You can say it's still a type of total CA, which means that we still need to calculate the sum of each cell's neighbors to decide the state of the cell after next tick, or we say at t plus 1. So simple majority rules, transition rules, they're like this. If one state is in the majority in a neighborhood, the focal cell included itself takes on that majority. What does this included mean? It means that when we're talking about simple majority rules in total CA, this total CA here should be an outer CA, which means that the cell itself needs to be considered when you are calculating what? Calculating the sum of the neighbors. So for a full cell Van Neumann neighborhood with 2 states, this rule is that if the central cell, if the focal cell is I, its state after 1 tick is equal to 1 if currently it is 0 and the sum of the neighborhood is larger than 2. It means that, be careful here, the focal cell itself should be included when you are trying to find out the majority. Okay, we're talking about Van Neumann neighborhood, which means that there are only 4 neighbors. But the cell itself should also be included in the counting, which means that the majority should be 3. If 3 cells, they are 1, then then after the next tick, the central cell should be 1. If 3 cells or even more cells they are 0, then 0 is the majority. And after the next tick, this focal cell should be 0. So if currently the focal cell is 0, but the sum of the neighborhood is already larger than 2, then we know that 1 is majority. Then after the tick, the focal cell should be 1. On the other hand, if the cell itself is 1, but simultaneously the sum of neighborhood is equal to or larger than 2, then you can still tell that 1 is still the majority. And after next tick, the focal cell should still be 1. The difference is that now the sum of neighborhood here can be equal to 2 because the cell itself is 1. Okay? It means that if the cell itself is 1 and the sum of the surrounding is only 2, then it's good enough. We still have what? We still have 1 as a majority among these 5 cells. Okay, 4 neighbors, and 1 is the cell itself. Okay, if this is not the case, then okay, 0 is the majority. Then the state of focal cell after next tick should be 0. And similarly, we can have this mathematical expression of the transition rules when there is more neighborhood. Okay, in more neighborhood, there are how many neighbors? 8 neighbors, right? But you should also consider the cell itself, which means that the majority is 5. If there are 5 cells or even more cells, they are equal to 0 or they are equal to 1, then 0 or 1 should be the majority. Okay. Okay. Before that, let me show you. This is model 3.3 from the model library, and here on the left side, there are just buttons for the model to set up, to run. On the right side are several functions I want to mention here. So here, neighborhood style, orthogonal. Obviously, this is von Neumann neighborhood. Orthogonal plus diagonal, this is what? More neighborhood, right? And Euclidean distance, this is using the real world distance to define neighbors. We'll just ignore this. In this class, let's focus on this too. So currently, orthogonal plus diagonal, this is more neighborhood, right? N size is 8. And on the right side, here we have the rule. The first column is for the number, the sum of the neighborhood plus the cell itself. The value could be from 0 to 8, right? And here, let's say we have 2 extra columns. They're representing the current state of the focal cell. Okay, so here actually there should be, we have 9 cells, right? 8 neighbors and the cell itself. So totally there should be how many? 9 cells. Should be 10 results, right? From 0 to 9. From 0 to 9. But the problem here is that we have other 2 columns to show the state of the cell itself. That's the reason why here from 0 to 8, this first column, it only represents the sum of neighbors. The central cell is not considered here, okay? And the state of the central cell or the focal cell, it is addressed here. So currently it is 1. And if the sum of the neighbors is equal to 0, then the majority is 0. So here, each entry here is addressing the state of the focal cell after the next tick. So if its current state is 0 and the sum of its neighbors is also 0, the next after next tick it should be 0 because 0 is majority. Similarly, if the current state of the focal cell is 1 and the sum of neighbors is also 0 and the majority is still 0, it should be 0. Okay, so here when you finish this list, you are actually giving rules to this model. So here you can use these two boxes to input your rules. List 0 is for the column of 0 for current state, and the list 1 is for rules of what? Of this column, right? When the current state of the focal cell is 1. So 0, 0, 0, 0, 0, 1, 1, 1, 1. 0, 0, 0, 0, 0, 1, 1, 1, 1. I actually input these two columns earlier before recording this video. So you can see that currently it's a typical majority rule. If the state of the cell itself is 0, and if the sum of neighbors is any value between 0 and 4, then the majority should be 0, right? That's the reason why you have 5 zeros here. But if the sum of the neighborhood is 5, 6, 7, or 8, even the state of the cell itself is 0, the majority should still be 1. Then after next tick, the state of the cell should be 1. Okay, you can do the same thing for this column when the current state of the cell is 1. So we have 4 zeros and 5 ones because the central cell itself is 1. So this time when the sum of neighbors is only 4, 1 is already majority. Okay, so here is how to use these two boxes to decide your rules. And there is indexing system. It's called Wolfram code. If you want to know more about the info about of Wolfram code, you can come to this info page. Okay, or you can go to the Wikipedia to there will be a lot of texts to tell you to explain what a Wolfram code is and how to produce it. But here I'll just tell you that for each specific list 0 and 1, you can what? You can find out a Wolfram code, and it's unique. This unique code is addressing this unique set of rules. You can have two list values to create a Wolfram code. Or if you have a Wolfram code, you input it here, you can click set from code, which means that the specific rules will be translated and listed here. Okay, but for now, let's just say we have these two lists, and using them, we have this Wolfram code 261632. This code is addressing this set of rules. Okay, now let's set up and go. So eventually, we have this stable state for all pixels within this space. Okay, so this is the spatial pattern produced from majority rules. This very typical one. Okay, and you can say there are aggregations of black areas, and a lot of them they are separated by white areas. So there are aggregations and there are also segregations. And we can say there are some black areas, they are locked in, or it's easier to find lock-ins for white areas. For example, this small island of white area here, you can say it is locked in. It is purely surrounded by black areas. It is called locked in. And yeah, you can say how a majority how majority rules they produce aggregation and segregation. Okay, and you can see this model is still running. It's more than 4,200 and 300 ticks, and it will stay this way because it is a stable state. I'll just stop it. Okay, it's the same. Okay, so this is the easiest way. This is the easiest, simplest set of rules for majority total, say A. Okay. And let's get back to our slides. Okay, and the majority rules behavior, they are very sensitive to the initial state of the system. What does it mean? It means that if the proportion of either of the two states, 0 or 1, in the initial pattern is low, it's very likely that the final system state will consist solely of the grid cells in the initial majority state. This depends on neighborhood size. The larger the neighborhood, the more likely that the initial majority state will dominate the final system. It means that it's pretty hard for the minority state to be dominant in the end if it is minority at the very beginning. Okay, so here we have four figures showing a lot of um, um, bar plots or bar charts. So here, in the first figure, the horizontal axis is for starting proportion of ones from 0.1 to 0.9. And the vertical axis is for the final proportion of ones when the whole system arrives at a stable state. So for this small neighborhood, a very typical von Neumann neighborhood, if at the beginning the proportion of 1 is 0, and then we say this this box plot here is a line, which means there is only one value. If at the very beginning the proportion of ones is pretty low, is 0.1, at the end the proportion of 1 is 0.0. It means that there will be no 1 in your final state of the whole system. It means that at the very beginning, 1 is minority. In the end, there is no 1. If there is a little bit more proportion of ones at the very beginning, for example, 0.4, it's still minority, but in the end, we have a very small box plot here, which has a mean value, has a max value around 0.2. It means that at the very beginning, 1 is minority. The proportion is 0.4. But in the end, the proportion cannot be 0.4 anymore. It's somewhere around 0.2. It means that it becomes even more minority, which means 0 is dominant. 0 is dominant at the very beginning because at the very beginning, the proportion of 1 is 0.4. The proportion of 0 should be 0.6. Now, the proportion of 0 should be around 0.8. It's becoming even more dominant. So this box plots, they're telling us that it's not likely that a minority at the beginning will be dominant at the end. It will still be minority. Okay, and if the neighborhood, here at least, from 0.1 to 0.4, at least it's possible that the proportion of ones will increase. To be dominant in the final state, not possible, but at least it if the proportion of ones is 0.4, in the end, one could exist, could survive, right? Right? Even the proportion is 0.2. But if we increase the size of the neighborhood, let's just check the last figure here. From 0.1 to 0.4, if that's the initial proportion of ones, when the system achieves a stable state, okay? Sorry, it's my cat. It will be 0 for sure. There will be no 1 because from 0.1 to 0.4, we have only what? Only lines, straight lines for box plot, which means that there is only one possible value, which is 0. Which means the larger the neighborhood you define, the more difficult a minority state will survive the majority rules. Okay, so that's the reason why we're saying that the majority rules, the majority total CA, they are sensitive to the initial state. The majority will become even more majority. Minority could survive if the neighborhood is not too big. If the neighborhood is defined as a huge, within a huge area, then you are pretty sure that the minority will die. Okay. And effect of neighborhood size. As the neighborhood size increases, the minimal stable clusters become larger and are less likely to form spontaneously. Okay, so let's get back to this. Okay, so this is a stable system within the space, and we have larger stable cluster and smaller stable clusters, no matter for white area or black area. So here what we're talking about is what? Minimal stable clusters. Okay, the size of minimal stable clusters is positively correlated with the size of the neighborhood. Okay, so that's another feature behavior for majority, for total CA following majority rules. Okay, and next we're going to talk about a special category, a special type of majority total CA. It's called twisted majority annealing. So the transition rules here, they are special. Okay, majority is one of the following sums. Now we consider more neighborhood and including the cell itself. When the sum is 4, 6, 7, 8, 9. These situations, they are considered majority, which means if there are 4 zeros, 6 zeros, 7 zeros, 8 zeros, or 9 zeros, then 0 is majority. It's the same for 1. If there are 4 ones, 6 ones, 7 ones, 8 ones, or 9 ones among the neighborhood and the cell itself, then 1 is majority. Obviously, there is something wrong here, because if there are 4 zeros or 4 ones, it's not majority, it's minority. That's the reason why this is called twisted majority annealing. This 4 here is wrongly but unpurposely taken into account. We would just say, okay, 4 is majority. Although this is against your common sense, but yeah, 4 is majority. And on the other hand, where is 5? If there are 5 cells with the same value, that value should be the majority. No, we dropped 5 on purpose. Okay, mistakenly include 4 and exclude 5. And why did they do this? This say it was proposed in from a paper in 1984 to simulate what? To simulate physics with cellular automata. It is trying to simulate a physical process called annealing. This is a term from blacksmiths. If you know a blacksmith, you know the meaning of annealing. I will show you its meaning later. But this is a majority rule. It's a twisted one because 4 has been included and 5 has been excluded. Okay, you can use a specific Wolfram code to give this set of rules to NetLogo to create this twisted majority annealing simulation. Okay, um, to set this simulation, and let's get back to NetLogo. Okay, this Wolfram code can be found here. Okay, when you input different Wolfram codes, you have different types of CA. Okay, so 261632, 261632. This is the code for the typical majority, normal majority rules, right? It's right here. It's right here. Now we're talking about twisted majority and Van Neumann neighborhood, right? Let's just double check. Or Moore neighborhood, okay, which means orthogonal and diagonal. 1 second. Yeah. Orthogonal and diagonal twisted majority. So the Wolfram code should be this. Let's copy and paste and set from the code. Okay, here we can say that 4 has been taken into account, but 5 has been dropped. Okay, this code is exclusive to this set of rules. Okay, let's just go. So let's say, what's the difference between this and the simple majority rule? Let's make it run a little bit more. Right, it's almost 1,000. Okay, it's stable now. We know, although there is changes along boundaries between black and white, but let's just wait a little bit more until 2,500 maybe. Okay, so this is the result of this twisted majority annealing. So what's the difference between this spatial pattern and the spatial pattern we saw before? There is no small locked in segregations. Although, yeah, we say that there are several small islands of black cells and white cells. But in general, we have large area, large region for black cells and large region for white cells. This is called annealing. And what is annealing? It's a term in blacksmith, right? So twisted majority annealing behavior makes convex regions unstable by forcing local reorganization at the boundaries. So this is an example of the specific simulation, right? And we can say at the very beginning, or not the very beginning, after 100 ticks, this is a spatial distribution. 400, 1,100. You can see that the shape of gray cells, or in NetLogo it should be black, but yeah, let's just say gray, is becoming smoother and smoother. At the very beginning, or at t equals 100, it's convoluted. All those aggregation, all those clusters of gray cells, they are convoluted with pretty complex shapes. But when the simulation goes on, you can say the aggregation, the shape of aggregation of gray cells is becoming what? Smoother and smoother, less complex and less complex. This process is called annealing, smooth boundaries due to preventing of log-in of early solutions. Okay, why is it? Let's just compare them. Let's compare them. Before I'm introducing the concept of annealing, this is simple majority. At the end, this is the stable state for the whole system. A lot of small aggregations of gray cells and white cells, and especially the shapes of gray clusters, they are complex. If you compare to this one, to the stable um, condition, stable state for twisted majority annealing, right? Only one huge aggregation, one huge cluster with a relatively simpler shape. Okay, and what is annealing? It's a heat treatment that alters the physical and sometimes chemical properties of a material to increase its difficulty and to increase its ductility, the ability to conduct electricity or heat, and reduce its hardness, making it more workable, which means reorganize all those items or molecules in the material, to reorganize them to make the material easier to work on. So we can just assume that this is organization of all those small particles at the beginning before the annealing is finished. It's everywhere. Let's just consider each gray cell here is a particle in the material. It's everywhere, right? And after annealing, they are getting together. They're easier. This material is easier to work on. So this is annealing. And this twisted majority annealing simulation is trying to simulate this physical process used in what? In heat treatment. It's a method of heat treatment. So you can say again, majority rules on it's a type of, majority say total say A. They belong to a type of say A, right? And it has no context. But some scientists, they use this simulation method without any context to simulate physical processes. Obviously, physics is a strong context, right? Okay, so again, that's a powerful part about what? Building blocks. And total CA following majority rules, they're building blocks, and they can be used to produce aggregation and segregation. And this is the result. This aggregation and segregation can be used in physics. Okay, yeah, and the third type of total CA I want to introduce here is called lifelike CA. A CA is lifelike if it meets the following conditions. Okay, the area of cells of the automation has two dimensions, which means the CA should happen on a lattice, two-dimensional lattice. Each cell of automation has two states, alive or dead, 0 or 1. Okay, anyway, two states, and it has more neighborhoods. If it is von Neumann neighborhood, you should not call it lifelike CA. And the new state of a cell is a function of the number of neighborhood cells that are in the live state and of the cell's own state, which means we're talking about an outer totalistic CA. It means that the state of the cell itself also matters. Okay, also matters. Then if all these requirements or say conditions, they are met, then this total CA can be considered as a life like say A. If you compare the game of life's rules to these requirements, you will say that game of life is a type is a life like say A. Okay, and we also have larger than life automata. It's called LTL. Okay, and life like say is specified in terms of critical parameters. They are still life like say A's, but when we're using different parameters to address a say A, we call it larger than life say A. Okay, and here these parameters, critical parameters, include P, beta 1, beta 2, delta 1, and delta 2. Okay, P is more neighborhood radius. Okay, usually we consider that in a more neighborhood, we have 8 neighbors. That is a more neighborhood with 1 as the radius. So if that's the case, P is equal to 1. Okay, okay, if your life say has a more neighborhood, of course it has a more neighborhood. That's one condition for a life say A, right? So usually P is equal to 1. Beta 1 and beta 2 lower and upper limits on the number of live neighbors for birth, which means that you should assign a specific number for lower limits and another specific number for upper limit. They are for live neighbors for birth, which means within this range, if the sum of neighbors is within this range and the cell itself now is dead, then it will what? It will be alive after next tick. So beta 1, beta 2, lower and upper limits on the number of live neighbors for the birth of the central cell. Delta 1, delta 2, they're also lower and upper limits, but on the number of live neighbors for survival. It means that if the central cell is alive right now, and it will survive after the next tick, then the sum of neighbors should be somewhere between delta 1 and delta 2. Okay, using these 5 critical parameters, we can define a very specific life say A, right? So for game of life, these parameters should be 1, 3, 3, 3, 4. It means that the more neighborhood radius for a game of life, say A is 1, right? And 3, 3, lower and upper limits on the number of live neighbors for birth. If the current state of the cell is 0, and it has exactly 3 neighbors alive for now, and then after next tick, the cell itself will be alive, okay? This is the lower and upper limits for birth. It's 3. It's only 3, okay? No other possible values. And the lower and upper limits on the number of live neighbors for survival, 3 or 4. Cannot be too many live neighbors. Cannot be too less live neighbors. Okay, if the central cell wants to survive after next tick. So it can be 3 live neighbors, it can be 4 live neighbors, but that's it. If there are only 2 live neighbors, the cell will die, cannot survive. If there are 5 live neighbors, too many live neighbors, the central cell will also die after next tick. Okay, so yeah, larger than life automata. It means that we use a specific set of parameters to describe the rules of life say A. Okay, I will just stop here. Section 3.3 has been finished. From next video, we're going to discuss using another method to create aggregation and segregation. Okay, we're going to talk about the simulation of interacting particle systems and say how to create aggregation and segregation by simulating these interacting particle systems. Okay, thank you.